data, a model, and loss. So first component, data. Where do we get data from? Well, I grabbed some data from the Finnish Meteorological Institute. Maybe I'll just show it to you. So I just Googled download observations from FMI. So I went to the homepage, download past weather observations, and you might use this data also for your project. So if you don't have an idea for a data source, use Finnish Meteorological Institute and weather data there. Then I choose weather observations. This is what we call also features. So what kind of properties we would like to use to predict something. So I choose here everything there is, daily observations, and so on and so forth. Then I select a time period, which determines the number of data points I read in. So if I have daily observations, then the number of days in this time period is the number of data points. Then I look up the station from which I want to download the data, and I click download. So that's how I get data. That's the first step. Not trivial step, but here in this case, it was straightforward. So now I go back to my Excel spreadsheet. So today I use Excel to do machine learning. And I have already prepared here some data I downloaded yesterday. So the observation data is here. This is raw data. Just look at raw data. What is data? How did we define data so far? Yeah, in this case, it could be days, but more general, what is a data set, or what is data? In a very general sense. Could be observations, yeah, features and labels, but features and labels already, yes, here is the answer that I wanted to hear, a set of data points. So data in a very general sense, but this is also very flexible way of defining data, is just a set of small units which are of the same type. And it's up to you that you define, and you should define it explicitly in your report. What do you consider as data points? It's up to you. There's no mathematical correct choice for what the data points are. What could be here a reasonable choice for data points? What could be a small unit of information, and so that we have many of these small units? When you look at this spreadsheet, you have already mentioned it in the chat. It could be a day. So I could say one data point represents one specific day. Like this data point here is the 5th of January. Another data point is the 4th of January, 2020. So from last year. Yet another data point, 18th of January, 2020. So one data point represents one specific day. Could be in the past, could be in the future. Of course, data points which represent days from the past, previous days, are somewhat nicer because I know more about them. But in principle, I can also define a data point being a day in the future, but I don't know so much about this future day. About the past days, I know something. In particular, I know I have now used only the air temperature. I guess it's a daily average temperature at some station. So then what kind of properties do we use to describe data points? We have two types of properties. Features and labels. So let's say the label, the quantity of interest, is the average daytime temperature. The average daytime temperature, because this is something that is important for ski waxing and choosing the right gear when you plan a day out. So let's say this is the quantity of interest. And then, but how can I predict this quantity of interest? Well, I need some other properties which I call features and which we can measure easily. And now I start already with modeling. So now I say, I consider the average temperature at a certain day as the quantity of interest. And as label, I consider the average daytime temperatures of the previous 1, 2, 3, 4, 5, 6, 7, 8, 9 days. Okay, from the last 9 previous days, from the previous 9 days, I define their average daytime temperatures as the features, which makes 9 features. Okay, so all of a sudden I have constructed 9 features for each data point. Well, not for each data point, because at some time someday I started to download. For this data point, for example, I don't know the features. However, could we find out the features for this data point for the 1st of January? So when I look at my raw data, I started downloading at the 1st of January. How could I find out the 9 label values for this data point if it's not here on my spreadsheet yet? Well, I got the data points from the Finnish Meteorological Institute, and I choose the time period starting 1st of January 2020. So I can just download the earlier days, because as I remember, the Finnish Meteorological Institute has recordings back 100 years. Yes, so I could download more data. Then there's one question: could you take from the next days? Well, in principle, I can say yes. I define the feature of a certain day being the average daytime temperatures of the future, of the 9 future days. I could do this. Remember, what you use as features is a design choice. What you use as label is a design choice. What you use as data points is a design choice. But why do you think it would not be a good idea to use as features the future 9 days of a data point? Well, if I want to learn, so the end goal of machine learning is to learn a predictor. That allows me to tell the average daytime temperature of tomorrow, which is tomorrow is the 9th of March. So I could use the features for this data point 9th of March 2021. I could use today, yesterday, and the last 6 days before. So I can use the features if I want to predict the average daytime temperature tomorrow. But if I would use the future 9 days, I could not use them because I don't know them yet. That's why it might be not practical for this application to use the future 9 days for the features. So let's say we use the previous 9 days, the average temperatures during the previous 9 days as the features of a certain day. Okay. And the average daytime temperature at that day is the label, or the quantity of interest. And now I want to learn a hypothesis. So what is a hypothesis? This already leads us to the second component of machine learning. The first component was data. Data as a set of data points. So we have here many data points. So each row here corresponds to one data point. So the first few rows are not complete, but then after the 11th row, we have complete data points. We have the label, and we have 9 features, a feature vector of length 9 for each data point. So data. Second component is, what is the second component in machine learning? What do we do with the data? We need a hypothesis, or a model. So a model is a whole space of hypotheses. So typically we have many, many different hypotheses. And what machine learning is about, give them a model, give them some model that is a set of different hypotheses, find the one that is most suitable. And I now show you how to do this in Excel. So my hypothesis is as follows, because I don't know anything more complicated. I say the label value of a data point can be approximated or estimated by a linear combination of all the features. So I define weights. So one weight for the first feature, one weight for the second feature, and so on. But then I include one, this is a special weight, which is just an additive or offset or bias term. which I add in the end. So I create then a hypothesis by saying I make sum product. Sum product means you compute the sum of all entry-wise products. So you take this feature, multiply it with this weight, W1, you take the second feature, multiply it with the weight W2, and so on and so forth, and then you sum up all these products. And finally, I add this W0 as an additive or bias term. So that's my model. This is how a model looks like in, oh, no, sorry, this is my hypothesis. I need to be more precise. A model is a whole set of hypotheses. So in this case, what you see here, this formula is for given values of W's. So if I fix all the values, I set some values here, is one hypothesis. If I consider the space or the set of all possible such hypotheses by using different values for the weights, this is a model, or this is a hypothesis space. And what now machine learning is about finding the best choice for the weights, or finding the best choice for the hypothesis. Yeah, is there anybody having the microphone on, wanting to ask something? Otherwise, I would ask you to mute your microphones, please. Okay, there were some questions on the chat. Yeah, very good question. So one question was, could you walk through how you came up with those exact weights? No, unfortunately, I cannot walk you through this because these were determined by Excel. And I will show you in a second how Excel provides methods that allow to try out different values for the weights and find the one which have the best or the smallest loss. And this already brings us in the third component of machine learning. We need an error measure. So once I have formed a hypothesis, which tells me, okay, I estimate the label or the label value by this weighted sum of the features, which gives me this output. So this value here, 1.82, is the predicted label. But the predicted label is obviously not the same as the true label. So I have a prediction error, and the question is, how do I measure? How do I quantify this prediction error? And for this, I need a loss. And here I use the squared error loss. So here, this column computes the squared error loss times some indicator. So we'll explain in a second what this indicator means. First, I check the chat here. So what are the weights in this case? Well, yeah, so I will show you in a second how to find the best choice for the weight. So I can set it at so I can choose one hypothesis, for example, setting all weights to 0. Setting all weights to 0, which is a very simple hypothesis which outputs always 0. So the predicted label is always 0. This is one specific hypothesis. And for this, I get some errors. Like in this case, the training error is 1, or the squared error, here it's 9. And in general, I will get a high error. So here, this cell here sums up the training error, and this cell sums up the validation error. And this already brings me to explaining this column here, train. So this column here, train, the elements are either 1 or 0. And if this element is 1, then this means this data point is included in the training set. And if this element here is 0, this means that this data point is not included in the training set, but in the validation set. So I want to show you how to split a data set into training and validation set into 2 subsets. And the way to do it is using a random generator. Yeah, by the way, you can find this spreadsheet on the My Courses page. So it's linked there. You don't have to now implement this yourself in Excel. You find, or even better, you should have downloaded this spreadsheet and follow me now in this lecture on your own Excel or spreadsheet software. So there's one question, is the test set included here in this validation set? No. So this now, the first step is to get 2 data sets, one for training and one for validation. And I do this by basically flipping a coin. So this function here generates, this function rand, generates a random number, which is uniformly distributed between 0 and 1. Then I compare it to some thresholds, 0.0. If this random number is larger than 0.0, it's 1. And if it's smaller or equal to 0.0, the value of this cell is 0. And then I copy this. And this I get, so I copy this formula, and in each cell, kind of this rand generates a new random number. So that's how you generate random numbers in Excel, which is pretty easy. And this way I generate indicators, either 1 or 0, and just copy the values. I then copy the values to get these selections for the training set. Okay, so now I have divided, or I divide the data points into either training or validation set. And I then use for the training error, the squared error times this indicator. So if this indicator is 1, then this here is the squared error. But if the indicator is 0, this cell here is 0 because this data point is not used for training. So let's look at another example where we have a 0 here. 0 means that it's not used in the training set, therefore the training error component is 0. Very good question now. How would you implement k-fold cross-validation? I don't know how to do this easily with Excel. So this, when I would like to use k-fold cross-validation, I go to some other program like MATLAB or Python. However, as I have promised to not require you to code, you get along with Excel, and it's fine if you use this single split into training and validation set for your project. You don't need to have you're not required, it's not mandatory to implement k-fold cross-validation in the project, because you should be able to get along with Excel. And here it's very convenient to do a single split into training and validation set. Yes, again, just to remind you, there's a follow-up course starting end of March, EJ 3211, called Machine Learning with Python. And there then we take the gloves off and do really machine learning in Python. Yes, so some other student pointed out that you could do something like k-fold cross-validation using nested ifs, but for example, I myself, I would not know how to do this easily, so I would also need to learn this. I'm not using that much Excel. Okay, so we now created the training and the validation set. So what I do now here in this cell, I sum up the training errors, and then I have I divide by the number of training samples. So I get the number of training samples just by summing up all these indicators here. Then I also determine the total number of data points I use now. This allows me to determine the number of validation data points, which is the difference between the total number of data points and the training set size. So I can then compute the normalized or the average error, squared error on the validation set by summing this column here. Okay. Any questions up to this point? Okay, so the training error function is computed here, and it's defined as, again, the loss function is a design choice. So I choose the squared error loss. So what I do, I take the true label, subtract from it the predicted label, compute the square of it. So this is the squared error, but then I multiply it by this indicator here in this column train, which is indicates if this data point is included in the training set or not. So by multiplying with this indicator, I zero out all the components or squared errors of data points which do not belong to the training error. And in the validation error, I do a similar, but I multiply not with the mask, the indicator here directly, but 1 minus this indicator, because 1 minus this indicator is equal to 1 if it's a validation data point and 0 if it's a training data point. So this is exactly the complement here. Yeah, so this is the training error, defined as the sum of the individual squared errors. So I compute the squared error for each data point in the training set and then sum it up. So this is the training error, or also called empirical risk in the literature. So what I do now, so I now want to find the best weights. So I need to solve an optimization problem. I need to search over all possible hypotheses. Each hypothesis is defined by a specific choice for the weights. But how do I do it? Well, I could try out, let's say 10. I now try out 10. Oh, this was not good at all. Training error is exploding. So this was not good. So I could try out. If I would only have a finite set of different weights, I could try out all and then pick the one with smallest training error. What is the problem? Why is this not a good approach to try out now all different kinds of values for the weights and then pick the one which has the smallest training error? So let's try out here one. Any ideas? Why is this not a good approach? Yeah, it takes way too much time because theoretically there are infinitely many weights, but of course we have only finite bit width here, so I don't know how Excel represents a number, maybe with 60 bits, but it's quite a lot. So we don't want to do that. And instead of trying out all different weights, we use optimization algorithms like gradient descent and so on and so forth. But in this course, we don't go into details of optimization methods. We just use it in some software. For example, you can use optimization algorithms in Excel. So you need the solver add-in, and I think for this you need to install some add-in, but you can Google it easily. But I have it now. So I go to help and then solver. And what I can do here now, I can use an optimization algorithm to minimize some quantity. So I need to define the objective with the quantity that I want to optimize. And in this case, it's the training error. So I choose the training error. And then I can choose the variables I want to adapt or adjust in order to make the objective as small as possible. So you cannot see my solver. So you now see this window here with solver parameters. Yeah, okay. So some of you see it at least. So now I choose the variables I want to tune or I want to optimize, which are the weights. So I choose it now, and then I click solve. And now this Excel algorithm searches over an infinite space of different weights. And now you see the training error goes down. Takes a while. Yeah, you will learn how these methods work, how the mathematics behind these algorithms is in optimization courses, particularly in convex optimization courses. So now it seems to converge. So as we now look at it, the algorithm is searching over all kinds of different weights, and it now seems to have found a good value. So there was one comment: shouldn't we use where is it? Shouldn't we use make unconstrained variables non-negative? Unconstrained. Unchecked. Yeah, that's a good point. So now I searched only over positive weights. That's a good hint. I didn't see this before. Yeah, we don't have any constraints. The weights can also be negative. In some applications, you might know that it doesn't make sense to use a negative weight, but here per se, we do not exclude negative weights. Very good hint. Let's see if it helps. Yeah, the training error goes down more. Because I have now a larger set of weights, I also now allow for negative weights. So the training error can only go down, but the validation error goes up. Yes, Excel is not a good tool for solving big optimization problems, but for illustration purposes, it's fine. I would immediately go to Python, but as I said, I don't want to confuse you for those of you who don't want to use Python in this course. You get along well with Excel here. So now, are we happy? We have trained a linear hypothesis. It seems that Excel has found a good choice for the weights. Training error is 3. Are we happy? We can already start diagnosing a bit because we also have computed the validation error. What is your diagnosis when you look at the training error and the validation error? Yes, it might be a bit overfitting because the validation error is significantly higher than the training error. So we have tuned these weights to perfect or to fit very well the data points in the training set. But the data points outside the training set, which are exactly validation data points, on those data points, it doesn't work too well. So it seems to have overfit a bit. How can we reduce overfitting? Yeah, we can make the model smaller. And if we use a linear model, making the model smaller means using less features. So we can fix the weights of features to 0 and only optimize over a subset of the features. So let's look now. So we now optimize only the first 6 features. We make the model smaller. Let's see what happens. What do we expect to happen with the training error? Yes, the training error is expected to increase compared to before. Yeah, it increased a bit. And also, I think the validation error went a bit down, but not too much. Yeah, there's one question. How do you measure significance of the difference in the errors? So there is no clear-cut answer to that. It's a lot of experience. But I would say if the validation error is more than 10% higher than the training error, I would try it. It might be okay in some applications. So if the validation error would be 3.3 or 3.4, it might be okay in some applications. But I would tend, when the validation error is 10% larger than the training error, I would tend to try something out to reduce overfitting. And there's already one comment in the chat for combating overfitting. We could also use regularization. And regularization is the topic of the Wednesday lecture. So on Wednesday, we will see how we can use regularization. And essentially, regularization works by not only directly minimizing the training error, but also taking into account properties of the weights. For example, penalizing large values of the weights. And we will see in the Wednesday lecture how to do this. Regularization is a very powerful toolkit, but we don't need it today. We will open it on Wednesday, in the Wednesday lecture. Okay, so then another question, what about the test set? How would we obtain that? I will discuss about the test set later. The test set we need only as soon as we use the validation error or the validation set to choose between different models. But up to this point, we didn't use the validation error to choose between different models. We just use it to monitor or to diagnose a method. Okay, yeah, so, but let's say we are happy, or now let's try one more. So let's make it even smaller, the model. So to reduce overfitting even more, we make the model even smaller. So we only use the first 4 features, set the rest to 0, or the weights of the others to 0, and only tune the first 4 and W0. So what do we expect to happen with the training error? Well, the training error goes up again because we made the model smaller. We made the set of different hypotheses to choose from smaller. Therefore, the training error can only go up because any training error that we achieve now, we for sure can only also achieve with a larger model. So the training error goes up a bit, but we also got the validation error down a bit. So we now move ourselves more and more close to having the training error on the same level as the validation error. Let's say we're now happy. It's okay. Validation error is typically always larger than the training error. If it's not way more than 10%, then it's acceptable. So are we now happy? Let's diagnose more. Are we now happy with our method? Did we crack the machine learning problem? Did we learn a kind of nearly optimal predictor for the daytime temperature based on the previous 9 days. What do you think? Is this average squared error of 3.4 optimal or close to optimal? Any educated guesses? If only one model was used, then no. Well, it's hard to say. We should check other models, or if anybody of you is a meteorological expert, then you might know. Based on the last 9 days, the error cannot be made smaller. There is currently no other prediction or forecast method with high accuracy. But since we are not FMI experts, or at least myself, I don't know. And that's why I ask you in your project to look at least one other model. And the other model is as follows. We again use the average daytime temperature of a day as the label, and the first feature is the same. So the first feature of a data point is the average daytime temperature the day before. But then I use different features and I construct features. So this now is an example of constructing features by computation. In particular, I take the power to the power of 2, second feature, to the power of 3, third feature, to the power of 4, first feature to the power of 4 is the fourth feature, first feature to the power of 5 is the fifth feature, and so on and so forth. Does anybody know how this is called, how this resulting linear regression method is called, where we use as features polynomials of the original feature or powers? Yes, that's exactly polynomial regression. So polynomial regression is a special case of linear regression, but using a specific construction of features. In particular, the features are powers of the original raw feature. The original feature was x1, the daytime temperature on the day before, and then we construct new features using powers. But I could use also the logarithm or the trigonometric functions. Any function I could use and construct new features. Only the sky is the limit for constructing features. However, why do you think it's not a good idea to construct arbitrary many features for a data point? Overfitting, yes. If you use too many features for data points, you will get zero training error, but you will not learn any good hypothesis. There's a very funny example. Just consider a linear regression model where you construct feature vectors with completely random numbers and a completely random label. If the number of features is larger than the training set size, you get training error 0, but you will not learn anything useful. Okay, that's why we stopped at the power of 6 here. This is okay to start with. And then I, again, do the same as before. I construct a hypothesis here in this cell. I compute the hypothesis by computing the weighted sum of all these features. So this is, again, a linear this form of the predictor or the hypothesis is exactly the same as in model 1. However, in model 1, I use the last 9-day temperature as features, and here I use different features. I use the previous day feature temperature, and then its powers as features. So I use different features, and that's why this is a different model, strictly speaking. Okay, and then what I do again is I optimize the weights. Same thing. So for each model that I consider, I tune the weights to minimize the training error. But again, here, this non-negative, I forgot. That was a very good hint. So I solve it. Let's see what happens. Okay, So I now tuned the weights to obtain a minimum training error. So I minimized the training error by choosing different weights. And at the same time, I computed the corresponding error, average squared error on the validation set. So are we happy with this? Let's diagnose again. Let's diagnose these methods. What can you tell from comparing the training error and the validation error? Yes, so risk of overfitting again, but there's also one comment, they are quite close to each other. So I go with that because I don't want to tune further. It's like around a slightly less than 10% higher. So let's say it's okay. So now I have a second model, which I have trained, and I'm somewhat happy that it's not too much overfitting. What do I do now? Which model to choose? Now I do model selection. How do we do model selection? Yes, we compare the models by their validation errors. So here I have 3.4 and here I have 3.5. Which one do I pick? Model 1 or model 2? Model 1, exactly. Easy. That's very easy. Model selection is easy. Just pick the one with smaller validation error. And now that I choose model 1, I have used up the information in the validation data points here, because I choose this model based on the validation error here. And that's why now this validation set is the same. So I have used the same split. I have used this validation set, the same set of data points for model 2 and model 1. And now, in some sense, I have now tuned the model based on the validation set, because I choose model 1 because it resulted in a smaller validation error. And that's why I cannot use this validation error of model 1 anymore as a reliable or fair estimate for the performance. That's why I now need a new data set which has not been used in the training or validation. And how do I do that? Well, I only use the first 254 data points for training and validation. And where do I get a test set from? Well, let's use some other data way below, which I didn't touch before, which I didn't touch for training or for validation. So here, these data points I use as test set. So I compute the average error there over this test set. That's how you get the third set. This third set is way at the bottom of this table. Training and validation has been done there, up there on the top rows, in the top 270 rows. And then I went more down and considered other data points as test set. So here's one question. Would you use the knowledge from model 2, which is that all powers larger than 2 are set to 0, to make a third model, which would be the last 4 days and each of them power 1 or 2? Yes, that's a good idea. Yes. And what you now did was diagnosing the machine learning method. And due to this diagnosis, which is, look, the optimal weights for W3, W4, W5 are all 0. So it seems that these powers are useless. But still, we might get a better model by using different features. So let's use as feature 1 the previous day's temperature, and as feature 2 the day even before, and all the powers of those two previous days up to power 2. Yes, that's a good suggestion. But for the project, we are done. So in the project, I ask you to compare 2 models. We are done now for the project. That's it. Then another question, how many data points should the validation set and test set have in relation to the number of data points in the training set? There's no general rule, and we don't expect you to argue why you choose that test set. I leave it up to you. A typical choice is to split 70% the training set and 30% validation set. And then if you have enough data, use the test set size being the same as the validation set size. But here we could use even more data for the test set because we have so much data points from FMI. So here, use as many as you can for the test set. The larger, the better. But in practice, there's often a limit because you need a good share of the data points for the training set. Otherwise, the training doesn't work. The training would be too noisy in some sense. So you need a good amount of data points for the training. And then the question is how much is left that you can use as validation or test it. But now here we use 177 data points for training. It seems to work well. So we believe that the training works. There are also ways to make a more finer diagnosis and check if the training worked well. So if the training algorithm itself is problematic, but this is beyond the scope of this course. This we will look at in follow-up courses, machine learning with Python and deep learning with Python. Then the question is, what is a good R2 score for regression problems? This depends on the data. So we had earlier asked the question, how do we know if this training error is already close to optimal? We don't know. We need benchmarks. A benchmark could be, for example, look at the average squared error that the Finnish Meteorological Institute predictions or forecasts have over the last 5 years. I don't know that, and I'm skeptic that they publish their errors. Another opportunity would be to get a benchmark is to assume or to interpret these numbers here as realizations of random variables. So we have this is a random variable and the features are 9 random variables. And then each row here would be a different realization of a random variable. And what we could do then is we could try to estimate the covariances between those variables. And once you have the covariances, you can use the R2 score to compute a benchmark. This is a benchmark. The R2 score is a benchmark that is based on the assumption that these labels and features of data points are realizations of random vectors. And once you know the probability distribution of these random vectors, you can calculate exactly what the optimal error is, below which you cannot go ever by any method, which is called the Bayes risk. But we will not dig into further detail here. There's a course called Bayesian Data Analysis, a follow-up course, which I recommend in this regard. Okay, another question. I'd like to try creating an image classifier in 2 steps. First step, feature extraction. Second step, comparing random forest logistic regression on the extracted features. Do you think this would be feasible? What would be a good loss function to use on the first part to maximize the probability of extracting useful features? Yes, so the first part, this is called an autoencoder. And as a loss function, you can use the squared error between the original image and the reconstructed image. But maybe for the scope of this project, you try to use for feature extraction, you use a pre-trained model via a pre-trained model which has been optimized on a large database. So maybe to keep it simple, use a pre-trained model where you don't have to learn anything and only learn the classifier, which is the core topic of this course. So this feature extraction, details on the feature extraction are beyond the scope of this course. We assume either the features are just given by reading in the data, or you construct them in some intuitive way. Like here are constructed features by saying, okay, I use for this data point here, I use the temperatures of the previous 9 days as its features. Or you use as features the previous day temperature and all its powers. So do not spend time on sophisticated feature extraction in this course. Another comment, looks like the test site is quite small here, perhaps from just a single month. Could this be the reason for the larger test error because the model doesn't work for that month? Yes, exactly, yes. So you already did a further analysis here. The test error here is larger is larger than the validation and training error. But for the project, this is fine. In the project, you just report the test error. You might comment, it's strange, it's larger, but I don't expect you to come up with solutions for this. And as one of the comment now pointed out, the problem here is that all these basic approaches like splitting into training and validation set and then splitting into a further subset test set, this only works if the data points have a homogeneous distribution. So each data point is a realization, an independent realization, or drawn from some fixed probability distribution. But here we use as data points consecutive days. So there is some time dependency. This is called non-stationary data, but we ignore this in this course. So in this course, you can consider these days as independent data points. Although this is not very accurate, but as it's a reasonable approximation that is valid for this course. Yes, so very good comment. I should have shuffled the data, but then to shuffle the data here in Excel, this would then be a bit kind of hard to grasp the spreadsheet. That's why I wanted to keep it easy. Yes, a cleaner option or a cleaner approach would be to first randomly shuffle the rows, mix them around. Another question. Would one ever actively choose the validation test set so that it would accurately represent the distribution of the data as a whole, or is using randomness always the best practice? Randomness is a good choice for fairness and for unbiasedness. So as soon as you handpick the validation set, there's a risk that even unintentionally, but you pick it favorable. And if you pick data points favorable for a validation set, then the resulting models might not be, you might not evaluate them fair or unbiased. So on some other data set, or if somebody else uses the method, might have a different, might obtain a different accuracy than on exactly the hand-picked validation set that you choose. So randomness is a tool for ensuring unbiasedness and fairness, objectivity in some sense. And it's always a good practice to randomly shuffle the data points before dividing them into training and validation set. But yeah, in this case, shuffling was not necessary because I generated these indicators that select data points either to training or validation set. I selected them using independent realizations of random variables. So the shuffling was basically handled here in generating these 0 1s completely randomly. If I would have said I use the first 100 data points for training and the second 100 data points for validation, then I would have done shuffling. But here I have chosen them based on this random order given by either 0 or 1. Okay, any